Good afternoon, everybody. Welcome to another exciting afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. Now, I was uploading it and somehow messed up. I messed up more than one way. I think when I rebooted my computer, I didn't realize that it shut off the video from last Wednesday. So this morning I did it again. I redid the whole thing without any students present, and I'll be uploading it right after class today. And then I'll also, after that, upload today's lecture. With that, let's get started. First of all, this Wednesday will be test 3. Test 3, hold on while I open it up. Hang in there. And if you guys should all be able to see it on the screen. Everybody see it? Good, thank you. On Wednesday, I'll be giving test number 3 online, just like 1 and 2. Sometime Tuesday, I'll be uploading it, probably afternoon, to D2L. You'll be able to download it. Right after class on Wednesday, I will be sending out the password for the PDF file. You'll have until Thursday, 10 a.m. to finish it and upload it as a single PDF file. It should take about 40 minutes, but if you need more time, go right ahead. But let me tell you, test 3 has 9 pages, 10 problems. Some of the problems are multiple part. I have never, ever in Chem 170 used multiple choice. It will cover carboxylic acids, esters, carboxylate anions, amines, amine salts, quaternary ammonium salts, amides, and heterocyclic compounds. Point breakdown, 7 points general knowledge, 30 points 38 points nomenclature, 60 points reactions. There'll be a couple synthesis problems under reactions, and it will have 5 bonus points. Remember, this is not an open note test, and you shouldn't also look online or talk to anybody else. I'll be doing a review today in a couple of minutes, and we'll have our regular Zoom meeting with our lab on Wednesday. Any questions about test 3? Going once, twice? All right, before I start the review, anybody happen to pick up a bottle of vinegar and think it has acetic acid in it, which is a carboxylic acid? Did anybody happen to pick up a bottle of nail polish remover and see it has ethyl acetate, which is an ester? Did anybody happen to pick up a bottle of ketchup and see it contains vinegar, which contains acetic acid, so it has a carboxylic acid? Remember, organic chemistry is all around you. I stole that from SpongeBob. All around you. It won't hurt to think about it. All right. Now, what I'd like to do today is, first of all, I'll go through the review for test 3, my world famous review. Next, I'll go through the problem set for amines and amides and amine salts and quaternary ammonium salts. And then I'll start on new stuff that will be on test 4 and not test 3, like I did on Wednesday when I talked about synthetic polymers. Like I said, for those who came in late, something happened to the video and I had to redo it this morning. I did my own lecture all alone. Yeah, I pulled it off, I hope. Well, you'll find out. And I'll be posting that right after class. It'll take about 2 hours, and then later on tonight or tomorrow morning, today's lecture Zoom meeting will be posted. All right, let's get to work. Everybody see test 3 review on the screen? Thank you. All right, let's start out. Carboxylic acids. Remember, when you're looking at an organic molecule, look for what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, because that's where all the action is. And here we have a carboxylic acid, carbonyl, carbon double bond to oxygen. That same carbon has hydroxy group and carbons. And the IUPAC rule is find the longest chain with the carbonyl carbon, name it as an alkane. Drop the E, add OIC in the word acid. Remember, the carbonyl carbon is always number 1. And any alkyl groups you name, like you name alkyl groups, but remember the carbonyl carbon is always 1. Now, there's some common names I'd like you to know. And on test 3, unlike the other test, because of the mean nomenclature, and I didn't teach you IUPAC, I showed it to you, I will have a different question and we'll say give the common or IUPAC names, but at the same time, I'll do like I've done in the past for draw the structure for the following names. And you should know acetic acid is a carboxylic acid where R is methyl. Formic acid, remember the fire ants, is when R in a carboxylic acid is hydrogen. Now, when R is benzene ring, IUPAC in their infinite wisdom said, well, we're not going to get these organic chemists change calling this. They've been doing it too long. So we'll use their name as IUPAC, which is also the common, and that's benzoic acid. Remember, everything you see on the screen is available to you in a file secretly named test number 3 review in the lecture section of D2L. All right, carboxylic acid is an acid. The hydrogen on the hydroxyl of the hydroxyl group is acidic. At a base, you form the carboxylate anion. M here can be lithium, sodium, potassium, be other things, but for this class, I'll limit it to that. A special base is sodium bicarbonate baking powder. If you take a carboxylic acid and react it with baking powder, this is a little different question. I asked, give all of the reaction products for this reaction, and that would be the carboxylate anion. Now this one, it picks up the proton from the carboxylic acid, forms carbonic acid, which immediately breaks down to water and CO2, carbon dioxide, and the arrow here shows you this is given off as a gas. And hopefully you all remember the little rocket ship story where my father taught me how to mix baking powder and vinegar, slam it, and it builds up pressure from the CO2 and goes poop, and didn't make any noise, but it would go about 4 or 5 feet. When you're 5 or 6 years old, that's really wicked. Even though back then they didn't use the term wicked, it was just something special. Also, don't forget, I hope you tried or will try my father's special little secret when making spaghetti sauce. At the very end, add a little sodium bicarbonate, because that reacts with the citric acid in the tomatoes and tomato paste, neutralizes it, reacts with the acid, and you'll see some bubbles, CO2. Remember that, it works quite well. All right, how do you make a carboxylic acid? I better ask, everybody still see the review? Good, Dr. White's on a winning streak. You take a primary amine and oxidize it, you'll get a carboxylic acid. If you take an aldehyde and oxidize it, you'll get a carboxylic acid. Remember, O in brackets means oxidizing agent. I'm not asking you to memorize those. Now, a really fun reaction is a Grignard reagent reacting with carbon dioxide. Remember here, X can be chlorine, bromine, or iodine. Second step, acid or water. The R group attacks the carbon of the carbon dioxide, and it forms a carboxylic acid. that's 1 carbon longer than the R group you started with. And this is a great way. And plus, this is that special thing or type of reaction where you form a carbon-carbon single bond. Very rare, very special. Now, next I start talking about a derivative of carboxylic acids. Derivative means made from, and that's an ester. That's where you have a carbonyl, carbon double bond to oxygen, with an R group, oxygen. On the oxygen is another R group, which we call R prime, just like X and Y in math. And how do you name them? Well, the IUPAC, first of all, you name R prime as the alkyl group it is in front. Now, the rest of it, the IUPAC way is name the carboxylic acid that would have been used to make that ester. Think of R prime as H, drop the IC in the word acid, and add ATE. Now, I had a very sharp student who said, for about most of it, except for when R is aromatic, a benzene ring, you can name the alkane that R plus the carbonyl carbon is, drop the E, add OATE. So you can either do A or B for 2. If you have R is a benzene ring, then you have to do B. Now, there's one important common name I asked you to learn for esters. That's when R prime is ethyl and R is methyl. And this nobody calls ethyl ethanoate, except when you tell people you don't call it that, because everybody uses the common name ethyl acetate. Nail polish remover. Now, carboxylate anions, how do you name them? You name the M plus, the cation, as the element it comes from and put that in front. For Na plus sodium, K plus potassium, Li plus lithium. And then use the same as number 2 for esters, which you can either use 2A or 2B or not to be. That's the question. Oh, I can't resist doing that. But anyways, either one of these will work, and that's how you do carboxylate anions. And guess what? I've already done this. Oh no, I'm doing the review. Dr. White just had a brain freeze. All right. No, I thought that because I went through this when I was doing the problem set for the video I did this morning. Hold on. Now my brain's back on track, I hope. All right, you should know esters are responsible for the smell of flowers and the smell and taste of many fruits and vegetables. If you smell and taste of a banana, that was an ester. If you like roses, you're smelling esters, and other flowers too, lilacs and so on. Now, how do you make an ester? Well, Fischer esterification, named after the great German organic chemist, Dr. Emil Fischer, who's also, I'll teach you, is known more for, this alone would have been a lifetime achievement, but he's also known for more widely his work with sugars. All right, take a carboxylic acid, react it with an alcohol in the presence of acid, H+, and you form an ester. The carbon with the hydrox group in R prime will be the carbon that this oxygen is bond to in R prime in your ester. Remember, for test number 3, and all of them, and the final, do you break carbon-carbon single bonds? No, you don't. Remember, that's your friend, and your other friend is this. How many bonds to carbon? 4. 1, 2, 3, 4. And that's always your friend. If you do something and you see 5 bonds to carbon, it's wrong. Also, Dr. White will laugh while he's grading it. One time I saw someone had 6 bonds to carbon. I almost fell off my office chair laughing so hard. 4. All right. Now, once you have an ester, what can you do? Well, you can react it with a ester with acid and water. This will come back to, because this is how your stomach breaks down fats and oils. And what do you get? You get back the carboxylic acid you would have used to make that ester, plus the alcohol you would have used to make that ester. The carbon with the oxygen in R prime will be the carbon in R prime of the alcohol with the hydroxyl group. Now, if you take an ester, and this is called saponification of the ester, and today we may get into why is that called that. If you take a base in water, can be lithium, sodium, or potassium, be other things, but for this class, I'm limiting it to that. You get back not the carboxylic acid like you see up here, because in the presence of base, this goes to this. You get the carboxylate anion of the carboxylic acid you would have used to make that ester, plus you get the alcohol you would have used to make that ester. Next, I started talking about amines and amine derivatives. Remember, this is something near and dear to Dr. White's heart because I have a number of patents in this area and help pay my mortgage, my car, and a whole lot of other stuff. Now, amines are where you replace the hydrogen on ammonia with R groups. And you have primary, secondary, tertiary amine, which I'll never ask on a test. Now, common names are used, so I didn't teach you that. Name each R group on the nitrogen as an alkyl group, and then add the word amine at the end. Now, there's one special amine you should know, and that's aniline. Aniline is where R in a primary amine is a benzene ring. This is one of those cases where, once again, IUPAC said, we're not going to change them. Let's just use the common name as the IUPAC name. And they did. Now, something very special and holy to Dr. White, quaternary ammonium salts. That's when you have 4 groups on nitrogen, has a positive charge. All molecules have a net 0 charge. Therefore, you have an anion. For this class, I'll use the halogens. How do you name it? Name each R group as an alkyl group attached to the nitrogen, and at the end, add ammonium halide. If it's chloride, Cl minus, it's chloride, Br minus, bromide, I minus, iodide. Now, amine salts are where one of the R on here, you have at least one hydrogen on the nitrogen, it's got a plus charge, and then you have 3 groups, R, R prime, and R double prime. And by the way, R prime and R double prime for amine salts can be hydrogen. And guess what? You name it the same as quaternary ammonium salts. You name each R group as the alkyl group it is, then add the word ammonium halide. Water break. Now, how do you make amines? If you take ammonia, react it with an alkyl halide, the non-bonding pairs of electrons attack the carbon with the halogen, you lose HX, which is why you need a base to neutralize it, and you make a primary amine. The carbon with the halogen is the carbon NH2 is bonded to. Remember, for amines, you have 3 bonds to nitrogen, but amines can actually quaternary ammonium salt, nitrogen, can use its non-bonding electrons to form another bond, and nitrogen can have 3 or 4. So it's a little confusing, but except for amine salts and quaternary ammonium salts, nitrogen has 3 bonds. Now, if you take a primary amine, 1R group on nitrogen, reacted with an alkyl halide in presence of base, you'll form a secondary amine. Again, the nitrogen lone pair attack. You take a secondary amine and react it with an alkyl halide. This attacks, and you form a tertiary amine. Now, there's still non-bonding electrons. I don't show them here. Dr. White's lazy. But if we take this and attack, a tertiary amine can attack another alkyl halide, or the same, presence of base, and form a quaternary ammonium salt. And now you're on hallowed ground, because it's a reaction that helped pay my mortgage and a lot of other things. And I'm a world expert in this reaction. Now, another way to make primary amines, which is a very excellent way, this was my first research project in the industry, nitrile carbon nitrogen triple bond, excess hydrogen, catalyst. Catalyst can be nickel, platinum, or palladium. Remember, this is 2 pi bonds, 1 sigma bond, any triple bond. And here, you break the 2 pi bonds in each atom of the triple bond, get 2 hydrogens, and you form a primary amine. Now, amines are bases. A base under Bronsted-Lowry is a proton acceptor. If I react it with HX and acid, you can do other things, but I'll stick to this class as HX, where X can be chlorine, bromine, or iodine. You have a proton transfer, and you form a salt, an amine salt. Now, for this one, remember R prime and R double prime can be hydrogen. So this works for both a primary amine, secondary amine, tertiary amine. A quaternary ammonium salt no longer has non-bonding electrons and is not a base. Now, new functional group, talked about amides. Amides is where you have a carbonyl with an R group. The carbonyl carbon is bonded to nitrogen, and on nitrogen you have R prime and R double prime. And either one or both can be hydrogens or can be carbons. How do you make an amide? You start with a carboxylic acid and react it with either ammonia, because R prime and R double prime can be hydrogen. When these are both hydrogens, ammonia, and you'll get this amide. And you can have these being carbons, one or both carbons, you'll still form amides. Now, once you have an amide, you hydrolyze it, react it with acid hydrolysis, acid and water. I'm going to stick to HCl because that's the acid in your stomach. And we'll learn later on, this is a general reaction, how your body breaks down proteins, which are amides, or amide linkages. And what happens is you get back the carboxylic acid you would have used to make that amide, but not the amine. Remember, amines are base. The presence of acid, you'll always get the amine salt. I don't have it here, but, well, it's up here. R prime and R double prime here and here can be hydrogens. Now, if we take a carboxylic acid, an amide, and react it with base and water, you won't get the carboxylic acid you would have used to make that amide, because the carboxylic acid in the presence of base will give you the carboxylate aniline, but you will get back the amine you would have used to make that amide. And I'll teach you later on, this reaction is a good way of cleaning out the hair in your drains, and I'll talk about this next chapter, the best drain cleaner that I use, as you can get it at Home Depot. I don't know if the other big box home improvements sell it. All right, last home stretch, heterocyclic compounds. You should know, what is a heterocyclic compound? It's a ring with carbon and other atoms, such as either oxygen or nitrogen. You should know What is a heterocyclic compound? It's a ring with carbon atom and other atoms, such as oxygen or nitrogen. I would like you to know the structure of only one heterocyclic compound, even though there are many, and this is pyridine. And if you remember, this was the compound, this reacted with something else, made the quaternary ammonium salt in my mouthwash. That keeps my gums nice and healthy. But this is pyridine. It stinks to all high heck, but it's a very important compound. Now, everything else I talked about, other heterocyclic and also alkaloids, that won't be on the test. I had the switch off for that. Any questions on the review? You know something? Dr. White could use a pick-me-up. So you know what time it is? It's time to play that fun game, circle and name the functional group, 2 points each. And that's where you get to circle and name the functional group, 2 points each. So let me get my whiteboard going. Look out, Dr. White is having a bad whiteboard writing day. And there you go. Have fun. Remember, this game is played by circle and name the functional group, 2 points each. Ooh. Do an extra bonus one. Everybody see the bonus one okay? When you're done, give me a thumbs up. All right, I think everybody's done. Anybody not, yell out. Okay, let's do it. All right, how do you play this game? You look for something different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention. Oh, look, oxygen here and here to the same carbon. Carbons. What do we have here? A carboxylic acid. Next, ooh, a nitrogen. Carbons here and here. This is an amine. Remember, our prime and our double prime can be hydrogen. Oh, we're not done. Oxygen here, oxygen here. Oh, there's carbons here, carbons here. What do I have? An ester. Let's, ooh, nitrogen here with 3 + 1 carbon, R groups, aniline. And what do we have here? And this is a quaternary ammonium salt. That's an ugly Q. And remember that's this right here. Oh, we're not done. Carbonyl with an oxygen and a minus charge and a cation. What do we have? A carboxylate anion, or you could also say carboxylate salt. I like anion personally, but either one is correct. And let's do the last one. I threw in actually second to last one. Carbon, nitrogen, carbon, hydrogen. What's this? An amine. Oxygen's here. Carbonyl, oxygen, carbons here, carbons here. What's this? Ester. And finally, more carbonyl with the nitro and carbons here and here. What's that? And this is an amide. Don't get amine and amide confused. Students get them switched and get them wrong. And remember, R prime and R double prime can be hydrogen. In this case, they're not. And finally, E. Ooh, nitrogen here and nitrogen here. If you look at this one, remember, R prime and R double prime can be hydrogen, and this is an amine salt. Oh, we're not done. Nitrogen here, carbons, hydrogen. This is, that should be C2. This is an amine. And remember, with an amine, you have R prime and R double prime can be hydrogen. In this case, they are. And that's how you play that fun game, circle and name the functional group 2 points each. I hope you all enjoyed it. It's such a fun game. Seriously, if you don't know what functional group you're dealing with, how can you name it? And how do you know how it reacts? So even though it's a fun game, it's a very important thing and skill to have. All right, hopefully you all see amines and amides problem set. Let's go into that. Remember, I'll do one page at a time. Haven't said this in a long time, but by now I think you might have figured it out. Remember, in my class, there's no such thing as a dumb question. Not only my class, anywhere in my life, there's no such thing as dumb question. But before I do this, quick commercial from Dr. White. Don't forget, Monday and Wednesday night this week, I'll have my office hours. So if you have any questions, stop on by. And I'm just a short Zoom internet away from you. Oh, that was awful. Remind me never to say that again. All right, let's look at it. Problem 1, give the IUPAC. Notice it's a little different, or common name. And I see I made a mistake in A already. Ah, boy. That should be N-butylamine. Correct that. A should be N-butylamine. Now, how do you do amine common name? You name the R groups on there and add the word amine. A should be an N-butylamine. Next one, B, you have, oh, I got that right, yay. Ethyl and isopropyl, there's no rule which goes first. You could have just easily put isopropyl ethylamine. Now, you should know this is aniline. All right, D, just cross off. Dr. White got overexcited, put stuff down he shouldn't have. All right, now, if we look at, let's do E. This is a quaternary ammonium salt. Remember the bracket here with a 2 tells you there are 2-methyl, 2-ethyl, diethyl, dimethyl. You could have dimethyl first. That's a quaternary ammonium salt, so we add ammonium chloride. Now here we have an amine salt where R prime and R double prime are hydrogen. I have N-propyl ammonium chloride. Now, if we look at B, we have start from the right, move left, and amine. We have, therefore, it's a nitrogen compound. What's on nitrogen? Ethyl group and tert butyl. It doesn't matter which side you put it on. Remember, for amines, there are 3 bonds to nitrogen, so we also have to add another hydrogen. C, cross off. Dr. White got too excited and shouldn't have put this. D, that's a very, very important molecule. When I say tallow, you abbreviate it by R sub T. So ditallow, dimethyl ammonium chloride. This is one way of writing it. Another way of writing it would also be correct. Would be that ditallow, dimethyl ammonium chloride. E, omit, and F, I think you can figure out. All right, let's look at some of the reactions. And if we look at draw the condensed structure for the organic product or products following the reaction, ammonia and methyl iodide, and here you'll make a primary amine. Remember, the nitrogen bonds to the carbon with the halogen. In this case, there's only 1 carbon. If you take a primary amine, react it with an alkyl halide, X can be chlorine, bromine, or iodine. This nitrogen attacks the carbon with the halogen and bonds to that, and you form this new amine. Now, special one. You take this tertiary amine, react it with this alkyl halide in the base, tertiary amine, alkyl halide, by the way, and this R and R prime and R triple prime, double prime are all carbons. You'll make a quaternary ammonium salt. And this is the quaternary ammonium salt that helped make me a lot of money. Notice Dr. White's smiling now. Now, amines are bases. This is a primary amine, but it could have been these 2 hydrogens replaced by alkyl groups, and you have primary, secondary, tertiary amine, HX, you make an amine salt. In this case, you add 1 hydrogen there. You don't have to show charges, and you do need to show the anion. And R here was methyl. I have a few more examples. G, cross off. I got over excited. I'm in one of my favorite areas of organic chemistry. By the way, this reaction, an earlier one I think I might have had, if you look at your cosmetics or personal care items and you see either ethanolamine, diethanolamine, or triethanolamine, that's added as a base to adjust the pH so it doesn't irritate your skin. Now, if we look at H, what do we have that's different? Ooh, carbon with a triple bond to nitrogen. Remember, 2 pi bonds, 1 sigma bond. Hydrogen and catalyst. Catalyst can be nickel, platinum, or palladium. Here it's nickel. Excess, because we don't like to balance chemical equations. You break the 2 pi bonds in each carbon of the nitrogen carbon triple bond, get 2 hydrogens, primary amine. And notice I don't break carbon-carbon single bonds. I have 3 here. I end up with 3. The carbon that was bonded to nitrogen now has 2 hydrogens. The nitrogen has 2 hydrogens. And if we look at J, I just gave you a much more scary R group. No, it's not scary if you know where to look for what's different. Nitrile hydrogen catalyst, break 2 pi bonds. Each atom of the triple bond gets 2 hydrogens. Now, if I take this and this in K, what is this? What's different? Carboxylic acid. What do we have here? An amine. Remember, for making an amide, R prime and R double prime, either or none or one, can be hydrogens. In this case, here's my R prime, and one of these hydrogens is R double prime. I'll form an amide. And notice this is the amide. R is methyl, R prime is methyl, R double prime, hydrogen. In an amide, like an amine, you only have 3 bonds to nitrogen. Here, R prime and R double prime are hydrogen, which they can be, and you form this amide. And here, same thing. Remember, the carbon with the nitrogen and the amine is the carbon that nitrogen is bonded to in the amide. Now, once you have an amide, you can do acid hydrolysis, and there you take an amide. Remember, R prime and R double prime can be one or both hydrogen, in this case it is, and you form a carboxylic acid you would have used to make that amide plus the amine, or in this case, amine becomes the amine salt, because in the presence of acid, amines and ammonia are base, and you form a salt. And if I look at the clock, I have a chance to do one more. Let's do P. Here our benzene ring will not react with acid and water, so this is an amide. And we have carbonyl, this is my R group. Notice on nitrogen, 1 is R prime, is hydrogen, R double prime is methyl, or vice versa. You get back the carboxylic acid you would have used to make that amide, plus the amine salt of the amine you would have used to make that amide. And with that, it's time to take a break. I'm going up and stretch because I need it. Dr. White did some serious battle this weekend with Mother Nature, mainly Sunday, and picked up some leaves, and boy, did my back pay for it. Ice pack last night a couple of times. With that, I'll see you in 5 minutes at 1:55. It's time to start again. All right, let's get back to where we were, and that's the problem set. And we had done acid hydrolysis of an amide. We'll come back to this later on the semester because this is how your body breaks down, or I should say your stomach, and I think it's your small intestine, breaks down proteins. And now if we look at right here, let's go down to this one, S. I was getting near the end of the alphabet. And if we look right over here, we'll see in the present, well, let's go back here again, just to be on the safe side. Remember, when you form an amide, react an amide with acid and water, you get back the carboxylic acid you would have used to make that amide, plus the amine you get from this hydrolysis reacts immediately with the acid because it's a base, and this is an acid, and you form a salt. And if we look at P, R, we have an amide. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Get your attention immediately. And here I have a carbonyl with nitrogen with carbon hydrogen. Carbon's on here because benzene is not going to react with HCl and water. Amide, acid and water. You get back the carboxylic acid you would have used to make that amide, plus the amine that you would have gotten forms the amine salt, which you can write in this problem. Either way works for me. Now let's move on. And now, if we look at S, what do we have? Well, benzene ring isn't going to react with base and water, but carbonyl, oxygen here, nitrogen to the carbonyl with stuff on it. Well, that sounds professional. And this is an amide. Amide, base water, base hydrolysis of an amide. And what you get back is the carboxylate anion of the carboxylic acid. Why? Because base reacts with the carboxylic acid to form the carboxylate anion, and you get back the amine you would have used to make that amide. Remember, R prime and R double prime can be hydrogen. They are an R, but let's look at S. What's R? Benzene ring, so you get sodium benzoate, and then the amine you would have gotten, R prime is methyl, R double prime hydrogen, add one more hydrogen, you get methylamine. And then, just to have some fun, I threw in some synthesis problems. And the important thing to remember, in certain synthesis, there's might be two different ways to do it. And if we look at, say, B, what do we have? Quaternary ammonium salt. I forgot the X here, and the arrow and the base. Wow, it all fell off here. And what do? You react a tertiary amine with an alkyl halide. In this case, X is chlorine. And therefore, I could call one of the methyl groups R triple prime, and the other one R double prime, and these two ethyl R prime and double prime, and it would be this. If I did it the other way and call one of the ethyl groups R triple prime, and then this R double prime and R double prime, one of the ethyl groups R double prime, this should be prime and R, I will use this. Either way would be correct. And finally, what do you react with hydrogen excess catalyst or excess hydrogen in a catalyst to form this compound? What is it? A primary amine? And the answer is a nitrile. Here's my R group. One of the things, remember, you end up with 3 carbons. I'm not adding carbons. I better start with 3 carbons. And that's the problem set. Any questions? Did anybody happen to think about a bottle of vinegar? That's acetic acid. Oh, I already did that. I knew I did. But anyways, those are things you should be thinking of. All right, any questions on amines, amides, quaternary ammonium salt? Oh, I forgot to do this. Did anybody happen to look at their fabric softener and think it's a quaternary ammonium salt? Or do you happen to look at your mouthwash and see the active ingredient, if you have scope or scope knockoff, is a quaternary ammonium salt? Notice, smooth, no static cling. I use a quaternary ammonium salt. Now, have you seen on TV the new commercials they have for the larger ones? Oh, it makes it softer. Yeah, you're adding 3 times as much quaternary ammonium salt. Then they've got the other one that helps make your clothes look newer. I've got to look up the patents on that and see how they're doing that. Should be interesting. All right. Well, in that case, guess what time it is? It's time for a new chapter and new stuff. And this new chapter is called Lipids and Detergents. Now, I should warn you, this chapter is going to get somewhat greasy and oily at times. I'm going to teach you something you never thought I would teach you about, how your hands get clean. And we're going to cover a lot of interesting stuff. Plus, I'm going to get into something you never, ever, ever thought Dr. White would talk about. So those are the coming attractions. I better get to work. Let me just clean up my All right, everybody see chapter 50 on the screen? Thank you. All right, let's talk about lipids. Now, what is a lipid? Lipid is a constituent, something found in plants and animals that are characterized by their solubility properties. They're soluble insoluble in water, but soluble in nonpolar. And I'll teach you later on this chapter what's polar, nonpolar, solvents like ether, hexane, even gasoline, but don't try that at home. So this is a lipid. Now it turns out, and by the way, switches on. This is material for test 4. Tabby subtle hint, know this. There are 2 types of lipids. One is called saponifiable lipid. The other is non-saponifiable. And hang in there while I turn off the spell check. Now, the saponifiable lipid is a lipid that can be hydrolyzed under alkaline conditions to yield salts, the carboxylate anions of what we'll teach you later on, fatty acids, otherwise known as carboxylate anions. Now, what does this alkaline mean? It means if you have a lipid reacted with base, like sodium hydroxide and water, one of the products you get are carboxylate anion of a fatty acid and other stuff too. Now, a non-saponifiable lipid, non meaning not, does not undergo hydrolysis under alkaline conditions. So if you take this, react it with base like this, and water, you get no reaction. So really, saponifiable lipids can be saponified to make carboxylate anions. Non-saponifiable lipids cannot react with base to make anything. Now, when we talk about lipids, what we're really talking about are saponifiable lipids. We're really talking about fats and oils. Now, fats and oils sometimes are called triester of glycerol, and sometimes they're called triglycerides. A number of years ago, when I started with this new doctor, unfortunately, he had to retire, but in the practice, they still have another really good doctor. And I went in and had my annual checkup. They did the blood test, and he said, I need to talk to you. Okay. And he said, the obvious, you have high blood pressure, you're overweight, and your triglycerides are too high. And he said, and I love this doctor because he knew I was a PhD organic chemist, man of science, which I am. And he said, guess what? If you don't change things, you're going to be dead in 5 years. And he showed me a study that would, when I was in the 5% or 95 percentile group, that with those things, you'll be dead soon. Guess what? I lowered all those. I still got to work on the weight, but my blood pressure is under control and my triglycerides are way lower. That means the fats and oils I consume. Now, the first question is, and hint, you should know this. And that is, what is a fat? Well, fat is a triglyceride that is a solid or semi-solid at room temperature. You don't have to know 25 degrees, but I thought you might wonder what's room temperature, and it's considered 25 degrees C. That's approximately, I think, 77 Fahrenheit. Now, solid, I think you know what it is, but a semi-solid, how many of you have ever had a dinner, fancy dinner? You have a stick of butter that's been out a long time. You stick your knife into it, you know how it's sort of soft? That's a semi-solid. Or if you want to get really semi-solid, next time you open up the jar of mayonnaise, stick your finger in there. That's a semi-solid. Now, don't do that, but you get the picture. And a salad, well, you know what that is. It's solid. Hold on, where's the solid? Solid. I should mention, if I'm having way too much fun, I've worked in this industry. I was the research director for all North America for a company that worked with fats and oils and made products from them. Now, what's an oil? An oil is also a triglyceride that is a liquid at room temperature. And therefore, that's an oil. I think most of you have seen either vegetable oil, canola oil, or olive oil. It's a liquid at room temperature. Now, if you put that in your refrigerator or freezer, it will become a solid. You don't have to, but if you did, it would. So oils are liquids at room temperature. Fats are solid. How many of you have ever cooked, say, bacon or a hamburger in a frying pan? You eat it and you left this stuff that came out, the fat, in there, and you forgot to clean it, and you come back. What do you see in there? A solid. Why? Because it's a fat coming from there, and the fats are solids at room temperature. Once the pan or frying pan cooled down, the fat would solidify. Now, what is a triglyceride? Well, let me talk about esters. Now, for synthetic organic chemists, we draw the ester this way. Now, fats and oils chemists, also known as I just have a mind freeze. Anyways, fats and oils chemists will write the ester this way, backwards, and they put the prime on this side. There's a reason. Now, what is a triglyceride? Well, tri means 3, and all fats and oils, and you should know this, have the following structure. Now, if we look at this right here, this is a triglyceride or fat oil. This is the structure of all fats and oils. The only thing that differs is what's R prime, R double prime. If you notice right here, I have an ester. Also that carbonyl, the oxygen here, ester. I have another one here. And I have a third one here. So there's 1, 2, 3 esters, which is why it's called a triglyceride or triester. So all fats and oils have this structure. Let me rewrite it. My mind just cleared up. And this would be the structure of all fats and oils. Now, people get confused, and there's a quite large professional society of chemists who deal exclusively in fats and oils, and that's called, I just lost my train of thought again. Wow, my head's, I gotta eat more fish, brain food. Whatever, I'll have to think of it again. But anyways, now I thought of the name. They're called oil chemists, not to be confused with oil from the ground. Those are called petroleum chemists. And in Champaign-Urbana, I think it's still there. I used to be a member long ago when I worked in this area. One of the large professional societies is the American Oil Chemist Society, where chemists deal with fats and oils and things you make from that. Soap and detergent and other things, mainly soap. Now, if you remember, these are esters. And guess what? The stuff we went through in the review, reaction of esters, fats and oils undergo. Just because you have 3 of them in a molecule doesn't mean they react differently. Now, let's talk about the reaction of fat or oil with acids and bases. And what you get is fatty acids for acid and glycerin. See, board. Ooh, I gotta get to work. Now remember, oil chemists write this backwards. Now I use sodium, hold on. I use HCl because that's what's in your stomach, and water. And as I taught you, but I'm doing it backwards from how I showed you. If you take an ester, reacted with acid and water, you get an alcohol plus the carboxylic acid you would have used to make that. So if you take any fat or oil, reacted with acid, YHCl, because that's what's in your stomach, and water, the first ester, what do you get? This alcohol plus this carboxylic acid. The second ester, what do you get? This alcohol. Remember, you don't break carbon-carbon single bonds, so these stick around, plus this carboxylic acid. And the final ester, ester number 3, you'll get this alcohol plus this carboxylic acid. And this alcohol, trihydroxy compound, has a common name, glycerin. And I worked for a company that did this reaction for different fats and oils to the tune of about 3 million pounds a week. Yes, 3 million pounds a week. That's a lot. And part of my job, which was quite rare for synthetic organic chemists, was not only did I run the research at that site, we also had a plant, and I was also in charge of all quality control. Not a fun job, but I learned a lot, and it was quite interesting. Now, this is an important reaction. Why? Because this is how your body breaks down fats and oils. If you had something like for breakfast, toast with butter, or if you had some bacon, or if you had a hot dog for lunch, or if you're a vegetarian, you had some olive oil in a salad dressing, once you swallow, by the way, I don't know if I told you this story. When I was real little, about 2 or 3, my mother said, chew your food before you swallow it or you'll choke. And guess what? I found out she wasn't lying to me. I did choke. Oh, by the way, I survived that, but in case you were wondering. But chew your food, like my mother taught me, and when you swallow it, it goes into your stomach, and your stomach has HCl and water, and it breaks down all the fats and oils to glycerin and carboxylic acids. We call those, and I'll teach you more about it today, fatty acids. Oh, that reminds me of another story. A number of years ago, I was driving through Willow Springs. You know, they have a train going through that. I forgot which main commuter line. And I was listening on the radio, and they shut it down, the whole line. And I'm thinking, what's wrong? And they said, well, we found on the track some open, broken bags of this dangerous chemical. And it turned out it was a fatty acid, which is totally safe. Your body makes it. And I pulled over because I was laughing so hard. I didn't want to get into an accident. About 2 hours later, they found out the stuff was quite safe, but the damage had been done to rush hour people trying to get downtown Chicago. Now, this is a general reaction when you react any fat or oil with an acid. Let's look at what happens with a base. Remember, I promised no new functional groups, and I'm keeping that promise. If I have, and I'll write it backwards like oil chemists do now to remember that name. And I'll use sodium hydroxide. And what you'll get is saponification of an ester. And you'll get back the alcohol you would have used to make that ester and the carboxylate anion of the carboxylic acid you would have used to make that ester. Well, if I have a fat or oil, guess what? I'm going to share because I haven't done it in a while. Why don't you try and figure out what would be the products of that reaction? And then I'll do it. What would be the product or products of this reaction? Your turn. Good news, I'm still recording. And when you're done, give me a thumbs up or the high sign. I guess everybody's done. At least 2/3 of us are done. JC, do you need any more time? I guess not. Let's go do it. All right, what do we have here? A triglyceride, which are 3 esters. Here's the general reaction of saponification of an ester. What do you get back? Ester number 1. You get back this alcohol plus this carboxylate anion. Ester number 2, you'll get back this alcohol plus this carboxylate anion. And finally, ester number 3, you'll get back this alcohol plus this carboxylate anion. And that's saponification of an ester. Why saponification? Because these carboxylate anions, when R is long, are prime, are prime, are double prime. There should be a double prime here. When R is long, say 12, 14, really 18, 16 carbons, these are called soaps. I'll teach you more about that. And in the old days, our ancestors would make soap by boiling fat, beef fat, or pig's fat with sodium hydroxide and water. And this is called, by the way, the old name for sodium hydroxide is lye. And they would make what's called lye soap. If you're using a bar soap at home in your bathroom or wherever else you put bar soap, I use it. I don't like the liquid soap for when I take a shower. That's carboxylate anions of fatty acids, and that's how they made soap. And that's why that reaction is called saponification of an ester because you would make soap. Now, I've used the term fatty acid. I'm never going to ask on a test what is a fatty acid, but I still should define it. It's a naturally occurring, in other words, Mother Nature made it, carboxylic acid that's always unbranched, straight chain, and always has an even number of carbon atoms. That's the R plus the carbonyl carbon. So here we have a fatty acid, which is short for fatty carboxylic acid. Organic chemists are lazy. We just dropped the carboxylic acid. And this carbon plus these are always even number. And generally it's from 12 to 26, more likely 14, 12 through 18. Now, switches on. There are two main types of fatty acids, and those are the carboxylic acids that come from fats and oils. One is called a saturated fatty acid. And a saturated fatty acid, by the way, Dr. White didn't even realize till now, this is abbreviation. See, I worked in this industry and I use slang. I should know this should be fatty acid. It's a fatty acid where the carbon chain, with a carbon chain, which all carbon-carbon bonds are single bonds. Saturated, remember we talked about saturated hydrocarbon? We have only carbon-carbon single bonds. Well, here it's where the chain has carbon-carbon single bonds. Now, you just can't say it's the molecule with only single bonds because you got a double bond right there in the carbonyl, but this is a carbon-oxygen bond. Now, I'm going to ask you to learn just one example, and you should know this, and that's stearic acid. And the structure of stearic acid, I'm going to do something I stayed away all semester, has 18 carbons, and now this means CH2 repeated 16 times, and this is stearic acid. And Dr. White worked for a company that made stearic acid, among other things. And this is a white solid at room temperature. And if on a test I ask draw the structure of stearic acid, you should be able to draw it this way. Don't waste your time writing 16 CH2s in a straight line. And if I ask what's the common name of the structure, you should know it's stearic acid. Now, since I worked in this industry, it's time for a little knowledge, real life knowledge, but first, this fats and oil stuff is thirsty work. Guess where you can find stearic acid? If you look at any high quality candle, 50% of the weight of the high quality candle is stearic acid. The other is, as I taught you earlier, paraffin wax. Now, there's a product that also has about 50% of the weight, stearic acid, by a company that's, I think, has since been bought out by Hallmark, but you'd have to, I don't know who owns them. But when they were alone, they were called Benny Smith, and I think they're the Benny Smith division. Any of you ever heard of the products from Benny Smith? It's Crayola crayon. Crayola crayons, 50% of the weight is stearic acid. The other is paraffin wax, just like candles, and they also put, obviously, a pigment in there. Now, when I worked for Unichem Chemicals, part of my job was if a customer was having problems, I got on a plane and went out and solved it. And one of our best customers for stearic acid was Benny Smith. That's back when they made it in the United States. I think they make them now in Mexico. Yeah. Anyways, one day the president of the company, United States, called me up. You got to be on a plane tomorrow to Pennsylvania. I forgot, it was outside of Pittsburgh. I forgot the name of the town their headquarters was. They're having a problem. Solve it. And by the way, in the chemical industry or people who buy chemicals, there's an old standby, I don't know if you call it method or trick. If you're having a problem that you can't solve, and you're buying, and it's using chemicals you buy from people, you call up that supplier and say, it's your stuff giving us a problem, come and solve our problem, which is what they did. Now, one of the more joyous things I had was to go there. By the way, I solved the problem, but I can't tell you that, or otherwise I got to shoot you. No, I don't. But anyways, when I got there with the salesman to their headquarters, they had this huge atrium, and hanging from all the ceiling walls were the winners of different contests throughout the United States, and I think even the world, but don't quote me on that, from kindergarten through senior year of high school, all their competition using crayons and their other products to draw pictures, and they were just amazing. And I got to see firsthand how they made Crayola crayons. It is amazing, beyond amazing. The problem I had to solve was they had come out with 4 new pigments. And upon sitting in the box for 2 weeks, the pigment migrated from the tip of the Crayola crayon, so it was white. Paraffin, wax, and stearic acid are white. And if you're a little kid, oh, what's the new color? And you pick it up and you see a white tip. Ma, I got a bad box of crayons. And the mother's going to call Benny Smith and let them know she's not happy. They don't want that, so I had to solve that problem. It wasn't our chemical, but we sold to the tune of about 5 million pounds a year of stearic acid. That's a lot of crayons, which they do. By the way, if you ever wonder how toxic stearic acid is, and that was the chemical that was in the bags that broke on the train, how many of you ever heard of kids or dogs and cats eating Crayola crayons and having a colorful ending? I'll let you figure that one out, and it doesn't get them sick. But it was a fun experience, even more fun after I solved the problem, going to Benny Smith. Now, this is a saturated fatty acid where all carbon-carbon bonds are single bonds, stearic acid. There are others, but I'd like you to know the structure of stearic acid. Oh, that reminds me. Well, I'll do the next one, then I'll tell you something. Now, you can have unsaturated fatty acids, and I'm going to ask you to learn the structure for monounsaturated. Unsaturated, remember unsaturated hydrocarbons? You have at least one carbon-carbon double or triple bond. Well, guess what? Mother Nature never, ever, ever, ever made triple bonds. That's something organic chemists did. So monounsaturated fatty acid is a fatty acid that has a carbon chain in which one carbon double bond is present, and that's oleic acid. And you should know this. Ooh, Steve bored. I better get to work. Like stearic acid, oleic acid has 18 carbons, this plus these. Notice at C9, carbon number 9, we have a double bond, which can be cis or trans. I'll talk about that in a second. And therefore, this is oleic acid. Stearic acid is a solid at room temperature. This is a liquid at room temperature. I'll never ask that on a test, but you might be interested in that. But on a test, if I ask, draw the structure of oleic acid, you should know how to do that. And same thing for stearic, you should also know that. So oleic acid has a double bond at C9, has a methyl group 7 CH2s, double bond, and 7 CH2s and a carboxylic acid group. And that's oleic acid. Now, next time you happen to pick up either some of your personal care products or your cosmetics, look and see if you see the term oleate, stearate, palmitate. That means those are esters from those fatty acids. And those are in a lot of your cosmetics. When I worked at Unichem Chemical, one of our better customers was Neutrogena. Have you heard of that company? And they make very high-end personal care items. And one of the things, because I worked with the people in Neutrogena, because we sold to them, they had very high standards for the quality of their raw materials, probably the highest in the industry, which they also charged you more because they had higher quality product. But those, they made a very nice product line, and I worked with them. Now, switches off on this slide. You can have polyunsaturated fatty acids where you have two or more carbon-carbon double bonds. I'm not going to ask you about that. Linoleic and linolenic are examples there. See, I worked in this industry, I know that stuff. Now, if you looked at oleic acid, you have a double bond. And remember, I taught you long ago, you can have a cis double bond when the hydrogens are on the same side of the plane of the double bond, or you can have a trans double bond. Now, where do these fatty acids come from? This right here is your R prime, and R double prime in your fats and oils, triglyceride. And based on what type of double bond it is here, if R prime and R prime and R double prime contain a double bond, or more than one, is it cis or trans? And if you followed medical science in the last 5-10 years, I think it's about almost 10 years now, you know that trans fats, medical science tells us, are bad for us, unhealthy. Cis fats in moderation, as my doctor always reminds me, are better for you, healthier. So whenever you go to the supermarket, next time you go to the supermarket with a friend, neighbor, or loved one, and you have them pick up a bag of potato chips or in the frozen section, some prepared meal, and it says on the front, it has 0 trans fats, you can tell them about the R group and the triglyceride. The hydrogens are on the same side for cis and opposite side for trans. People don't like hearing chemistry in supermarkets. Trust me, they don't. But think about it. Why does that do that? I have no idea. I have some theories, but they're just theories. But medical science has proved, and I believe the doctors who worked in those areas, that when it's a cis bond, double bond in the fat or oil, R group or R prime or double is healthier for you than trans. And obviously the food companies believe that too, or they wouldn't have spent all the money to switch over to cis fat products. I think, don't quote me on this, but I think both Burger King and McDonald's, and I don't know if KFC, all use now for a number of years cis fats to make their French fries. And if you look at, interesting story. A number of years ago, I was driving to ECC, and I was just getting off at McLean, going to the campus. There was this huge semi for Frito-Lay, and they had Lay's potato chip on the side, picture of it, or painting, on the side of the semi. In the upper corner, and this is when it was real hot, 0, said 0 trans fat. So I looked at that and started laughing. I said, I'm probably the only one on this road right now who sees that and understands what that really means chemically. But now you do too. See all the neat stuff you learned in my chemistry class? By the way, I should fess up. One of the most dangerous comfort foods in my life is the sour cream and onion Lay's potato chips. Open a bag and they evaporate like that. They just disappear. I don't know how it does it, but they just disappear like that. Oh, wait, let me get the crumbs off my hand. But oh, do I love them. And I only buy it a couple times a year, my birthday, New Year's. Also bought it for the election because I hoped someone would win. And when they finally, days later, I opened that bag and celebrated that and something else organic as a hydroxyl group. Oh, look at the clock. I'm gonna give you an extra minute. Come back at 2:50. We'll continue on with our adventures in fats and oils. I'll see you in 5. I'm back. Quick question. Has that irritating noise been gone most of the time?
I think it hasn't been super noticeable. When you said that though, just now it was back.
Yeah.
It just came back?
Yeah, right now.
Should get my mouth shut. All right, I'll figure out someday what it is. I've tried a number of things, so it's not the light because it's back now. All right, let's get back to work. We're talking about fats and oils and cis and trans. And you should know that what's the difference between cis and trans, or what's cis and trans fatty acids? That's, you can have a double bond here that can be cis or trans. Now, one thing I should point out, what's the difference between a saturated fatty acid and monounsaturated or unsaturated fatty acid? Double bond. Saturated, no double bond, carbon-carbon double bond. And in saturated, you have at least one present. In oleic, which I only asked you to learn monounsaturated, you have one double bond, which can be cis or trans. Now, time to teach you stuff that's not even well in the book if you're reading the book, because I worked in this area quite extensively. So I'm going to teach you some stuff, a few things you should know. So let's go back. Now, when it comes to fats and oils, they're different type. Now, you call it beef fat, we don't. Everybody see the slide with beef fat on there? Thank you. Beef fat, you should know, is called tallow. And the highest grade here, which you don't have to know, is BFT, stands for bleachable fancy tallow. That's the best grade. Now, pig's fat is called yellow and white grease. And you should know pig's fat is yellow and white grease. The difference, white grease is a little more expensive because it has a little less yellow color to it. All right, what just happened? See if I got my whiteboard back. Oh, come on. Say Friday the 13th yet? Let's try this, go back to this. All right, why that does that, I have no idea. Let me just check. Everybody see BFT and beef fat and all that? Okay. Now, these two you should know. If I ask on a test, what is tallow? You should know that's beef fat. If I ask what's white and yellow grease, you should know that's pig's fat. Now, in the real world, beef fat is a couple more cents per pound than pig's fat. If you're buying 100 million pounds or more in a year, you try and use pig's fat whenever you can, even though the supply is higher for beef fat, because we eat more beef than pigs in the United States. And I worked for a company, we got combined, like I said, about 3 million pounds. How many of you have ever seen a tank wagon, the vehicle that delivers gasoline to the gas station? And those are only, why is the sun, hold on. This is playing games with me again. All right, hold on. There we go. Once in a while, I've got so many things running on this computer, it plays games with me. All right, let's open up the all right. You all see the me? Now let's try this. You see beef fat on this? All right, finally, certain things weren't popping off. All right, you should know that beef fat is tallow. So if on a test I ask you what's tallow, it's beef fat. And if I ask you what's yellow grease or white grease, it's pig's fat. Now, if you're cooking, you call it lard, but we don't cook with that in the chemical industry. We make stuff. Now, some other things, which I won't ask you, but you're familiar with, you can get coconut oil, soybean oil, corn oil, also mixed with other things called vegetable oil, olive oil, and then this, wow, this is a weird name, rapeseed oil. Now, throughout the world, especially in underdeveloped countries, instead of using vegetable oil or very expensive olive oil, they use an expensive rapeseed oil. Now, what is rapeseed oil? It's oil pressed from the seeds of the rapeseed plant. Now, where is it grown a lot? In Canada. Now, when they tried to sell that in the United States to American housewives, rapeseed oil, I don't want any part of it, go away. And someone very smart up in Canada in the marketing part of the oil producers in Canada, vegetable oil, rapeseed oil, said, I don't know if they said, but they said, well, we can't get them to buy it with that name. Let's see, it's made in Canada, it's an oil, let's call it canola oil. Everywhere else in the world, it's called rapeseed oil. In the United States, it's called canola oil because it comes from Canada. And then people say, oh, that's not too bad, I'll buy it. And if you go in your local grocery store, you'll find in the oil section, cooking oils, they'll have canola oil, which is usually lower cost than vegetable oil. Now, I'm going to turn the switch. Will this be on? A test to the off position. Here's some standard, nobody uses IUPAC names in fats and oils, fatty acids. When you have 12, it's lauric acid, 14 mystic, 16 palmitic, stearic, I don't even know how to pronounce this one, Oleic is 18 with a double bond. Linoleic is 18 with 2 double bonds. Now they say cis and cis. No, some of them are trans. The person who wrote this didn't know what they were talking about. Linoleic, 3 double bonds. Now, interesting thing, let's look at palmitic. True story. I worked for a company, Axo. At that time, they also dealt with fatty acids because Axo, which was Armac, started from the Armour Meatpacking Company. And back in the 1920s and 30s, Armour in Chicago did a lot of slaughtering of cattle and pigs to make meat that they sold. You've heard of Armour ham and things like that. And at the end of the slaughtering process, they had 2 things they didn't know what the heck to do with. One was the blood, the other was the fat. And the blood became Armour Pharmaceutical because they made medicine out of that. What, I don't know, but they worked on that. And the fat became the company I started working for decades later, Armac, which was short for Armour. And I forgot what the MAC stood for, but anyways, I was lucky enough to have mentors who actually helped start the fats and oils amine industry because they took the fats and made them into amines, and then fabric softeners, quaternary ammonium salts. One of them was Sid Shapiro. Another one I got to meet and know at the end of his career, Ralph Potts. And these were giants in terms of what they created. And it was always interesting hearing about what they did. And one of the stories, and let me get to my whiteboard. In World War II, the military Air Force was looking for a serious weapon that was quite lethal. And what they're trying to do was make this explosive gel that once you lit it, stuck to your skin and did serious damage to the enemy. And if you ever take water and oil, they don't mix. Well, you use what's called a surfactant. I'll teach you about that. And Armac was known for being the leader of surfactants. And if you take a fatty acid, react it with sodium hydroxide and water, where this is a fatty acid, you make a carboxylate aniline. In terms of, and don't try this ever at home, take water and gasoline and put in some of this carboxylate aniline, it forms this gel, which is very flammable and sticks to skin. Now, you know it as, and I think it was Ralph Potts who came up with the name for it. And how did they come up with napalm? Well, the R group in carbon came from palmitic acid, and this would be sodium palmitate, which is how you use the common name for palmitic acid. And Ralph said, oh, sodium, Na, take the palm, put it together, and he was the one who named napalm, which is now made differently, but back then, that's how they made it. And like I said, always, there are good things to organic chemistry, and some things that are, I don't know if you call it not good, but not life-saving or enjoyable, but still necessary. Now, switches off for this slide. If you look at this slide, I just thought I'd point out, if you look at the animal fats like lard, which is really tallow, and you can see the person who wrote this chart have beef tallow. You can't have non-beef tallow because tallow is beef fat. Well, anyways, you notice over here, the bulk of the fatty acids that come from saponification of the triglyceride are saturated acids. If you look at, say, beef fat, it's about 52%, 55% saturated acid. And here for tallow, 42%. It's actually closer to 50-50, my experience. Now, if you look at the vegetable oils, which are liquid at room temperature, those are mainly unsaturated fatty acids, have double bonds. And that's why I believe, medical science has said saturated fats are bad for you because they help clog up your arteries, where the unsaturated are liquids and don't clog it up. Am I right? Probably not, but it's a good indication. So if you look at olive oil, which is the healthiest of all vegetable oils, it's the highest in unsaturation. All right. I said I wasn't going to do a new reaction, but let's talk about hydrolysis, also known as splitting of a fat or oil with steam and seaboard. So let me get to my whiteboard. Now, before I do this, in order to give a real life situation, most chemicals used come from tallow or white or yellow grease. And when I worked in, they still probably do it, at Unichem, we could switch white or yellow grease with tallow most of the time. And what does that mean? How can I give you a realistic feel for the chemistry that's going on? And they still have a plant near the old Comiskey Park for real life chemistry. Well, I came up with an idea that'll give you a good approximation. For tallow and white grease, use this structure. It's a triglyceride, all fats and oils are. And for tallow or white grease, yellow grease, we're talking about a fat. Now, this is approximately a 50-50 of saturated and unsaturated. And saturated would be R sub S, sterol, which makes stearic acid, and unsaturated would be R sub O. How do you have three things make 50-50? You can't. So I figured I'd just, for our fun, do this. And notice the letters on here, Dr. White's joking again, SOS. And if you know what that stands for, save our ship. But in real life, this is a good approximation of tallow and yellow grease right here. And what do I mean by R sub S? This would be stearic acid. As you know, this is stearic acid. And what I mean by R sub S is this. And R sub O is for oleic acid. And here we have oleic acid. And when I say R sub O up here, what I'm really meaning is this is R sub O. So if I ask on test certain things, we'll do, this is the structure you should use for tallow, white grease, or yellow grease. So let's go back and look at what we were looking at. And let's look at, first of all, this is a variation on a reaction you already know. Now, I showed you if you react this with acid and water, what's the acid? A catalyst. Now, if I use steam, what is steam? It should end in about 3 more calls because one more. I'll write this while it's making noise. Stop. Thank you. All right, steam is very hot water. Now, if you remember from your general chemistry, how do you make a reaction go quicker? Well, there are 2 important ways. One is you add a catalyst, and you've seen that all semester. You add acid catalyst or base catalyst for some reactions. What's the second way? Well, there's a rule of thumb, see it's on that thumb, which means it's 90% true, and for this reaction it is true. Every 10-degree increase in the reaction temperature doubles the reaction rate. By making the temperature you do a reaction hotter, it makes it go quicker, which is the same as like adding a catalyst. So at the company I work for and other companies, instead of using acid catalyst, we use steam, which is very hot water, high pressure steam. Oops, the R fell off. And what you get is the same as acid hydrolysis of an ester. You get back the alcohol plus the carboxylic acid you would have gotten used to make that ester. So if I take tallow or white grease or yellow grease, which I'll designate like this, and add steam, you get back first ester, an alcohol, plus the carboxylic acid, and here is our sub S, stearic acid. Second alcohol here, you'll get, or ester, you'll get this alcohol. And notice the R group is R sub O, so I'll get oleic acid. And finally, the last one, which could be R sub O or R sub S. How do you do 50-50? I just artificially did this. You'll get this last alcohol plus stearic acid, which I could write either a 2 up here or, and really what you're making is stearic acid, oleic acid, and glycerin. And we purified the glycerin. When it's impure, I don't know why it was called this, but they call it sweet water. We purify it, distill it, purify it, and sell it. And it's a valuable chemical too. Sometimes we made more on the glycerin than the stearic and oleic acid. And that's what we would make. So if you take this, and this is called, and we would call it splitting, because you split the fat, we would do this reaction to the tune of about 2 to 3 million pounds every week. If you look at a tank wagon that delivers gasoline that's 40,000 pounds. 10 would be 400,000. 50 of them would be about 2 million pounds. We got both tank wagons in a fat and also railroad cars, which hold 4 or 5 tank wagons full. We got a lot of fat in every week. And the company I worked for bought the chemical division from the Darling Rendering Company. You probably don't know what a rendering company is. Have you ever heard of rendering fat to make the liquid from skin? If you know Eastern European or Jewish cooking, you do that with chicken fat, you render it. And certain recipes, you do beef fat to render it to get that to use in your recipe. Well, anyways, a renderer, and I'm glad I never worked for one, but on our site, until they finally closed it down, I had left by then, but there was the Darling rendering plant. And a rendering plant would get from slaughterhouses and butchers, slaughterhouse, the bones and whatever left over from the slaughtering, fat and blood, and they'd heat it up, get the fat out, separate the blood, the bones they grind up and sell as bone meal for chicken feed, other animal feed, and we would buy the fat from them and other companies too. And it was one of the worst smell places. In the chemical industry, I got used to every smell except the rendering. Luckily, my office was upwind, so I never got that smell too often. But do I have, oh, I do. It's time for an interesting Dr. White story. Now, if a cattle died before it was slaughtered properly, they couldn't use it to make meat from. And they just shipped the whole thing to the renderer. And they'd have these open trailers come in the summer, it stunk. In the winter, well, one winter I was lucky enough I could do my own flex time. I used to get there about 6 in the morning, so I beat traffic on the Dan Ryan and the Eisenhower Expressway. Well, because I was a senior manager, we had special inside the plant parking that was covered. So I'd have to drive through the guard post. The other employees had employee parking lot, but I'd drive into the plant and I'd go to my special reserved parking spot. Well, we'd go by the rendering plant. I would drive in by our plant and go to my parking space. One morning at 6 in the morning, I'm driving in. Guess what I see in the middle of the road? I could drive around it, but a dead cow on its back with its legs stuck up. If you ever saw Animal House with the horse, well, this was it. Well, I knew the manager, plant manager for the rendering plant because I had to deal with him for other reasons. I get to my office after I park my car and say, call him up, and I think his name was Bill. I said, Bill, we got a problem. He said, what? What do we do now? I said, guess what? Right past the entrance in the road, there's a dead cow. And he laughed. It was like 10 below. It was frozen solid. He said, I'll send a fork truck out there. And he did, and it got rid of it. But that's rendering plant. Now, this is a chemical legend, which I don't know if it's true or not. But how many of you have heard of Jimmy Hoffa? Jimmy Hoffa was a labor leader in Detroit who was crooked, worked with the mob, supposedly. And after he got out of jail, after being convicted by Robert Kennedy, I think he was up for I don't know how many years, he went back to Detroit and was trying to get back into the Union and also being corrupt. Well, he disappeared. And everybody knew it was probably a mob hit. And to this day, they've never found his body, which is sad, but true. And one story I heard was he was taken to his body. Is this true or not? I have no idea. To the Darling rendering plant. And once you render a body, there's nothing left to find. It's gone. There's nothing you can prove. Please. So did it go there? Who knows? But it's an interesting story. Oh, another story. If I have time, we're doing good time-wise, so I can hit you with another. When I was working at Unichem, the president called me up and said, well, I know you're Jewish and you from Chicago. Could you find out, can we sell our glycerin as kosher glycerin? If you're not familiar with kosher in the Jewish religion, there's a dietary laws. Muslims have halal and similar. I don't know if it's the same, but similar. And there's certain things you can't eat and there's certain things you can't mix. Like you can't mix anything from milk products, dairy, with anything from meat. You also can't eat anything from a pig, anything from, let's see, certain shellfish and other laws, dietary. And immediately I told him, well, are you ready? You're going to spend a couple $1 million and build a separate plant? Or are we going to go exclusively on beef fat, tallow? I said, no, are you sure? I said, hold on. And at that time, cousin of my third cousin, my mother's first or second cousin, my mother's first cousin, I knew him quite well, Paulie, was the head of the Chicago Rabbinical Society. I called Paulie and said, who do I call to find out? I think I know I'm right, but he said, oh, you want the Union Orthodox rabbis here in Chicago? Here's the guy I know. Tell him you know me, you're a relative. He'll talk to you. I talked to him and he confirmed what I told him. But in case you're not used to kosher to this day, I also believe it, things that are kosher are made to a higher standard than things that are not kosher. How can you tell that? Well, there's a secret that's not really secret. Everybody see symbols on your screen right now? All right, the most widely used kosher symbol is the circle U right here. And that's for Union of Orthodox Rabbis. This is for Keruth, and I forgot, different parts of the country and the world use different. Here, this is the Hebrew letter that begins in kosher. They put a K in there. Here's another one. But circle U is probably the most widely used in the United States. See my pop bottle? You see right there? The circle U? My pop bottle, or not pop, water bottle is kosher. What that means is anything made in there has been certified by the Union of Orthodox Rabbis, and I called, and they confirmed, the head of that confirmed, no, you were right. And I told the president, as long as we buy pig's fat, you can't ever get it kosher unless you build a separate plant that's only tallow, which we never did. But it was a good idea because you get a lot more when you have kosher grade products, raw materials, people pay a lot more. Now, interesting story a while back that was in the Wall Street Journal. And back when I was at Unichem, I got the Wall Street Journal, and I'll explain why I was on the circulation list at our company. I'd read certain parts of it. There was a story about this food flavoring company in China who sold different flavorings or spices or whatever and wanted to get kosher certification. Because once they got kosher certification, they could charge more. So they called up and got the Union Orthodox rabbis. They paid for someone to fly to China and inspect their company. They walked in, looked around, and said, I can't. Why? Your workers are eating pork. You can't have any pork on the site. So, because of the amount of extra profit by having kosher certification, the owner of that plant got all his workers never to bring any pork. I think he provided lunch for them afterward. They had to pay a nominal amount. And then a year later, they had a guy come back. He inspected, all right. And then he also came back on a secret inspection, pop inspection. and they got their kosher certification. Next time you happen to be in a supermarket, look at things. True story. After I told this, I had a student say, oh no, and she was Muslim, and the kosher laws are similar to Hoffa, which are their dietary laws. Hope I'm pronouncing it correctly. Sometimes I mangle it. But she said, oh no, does that mean I have to stop eating Oreos because it's not kosher? I said, wait a second, go look at the bag. If you look at the bag of Oreos, you'll see in the lower corner, there's a circle U. And a lot of other things. You'd be surprised how many things have kosher certification, because there are a lot of people who are not Jewish. Look for that as an indication of higher quality product. By the way, the best hot dogs are kosher. None of that other stuff. And I better get back to work. Now, I'm going to have you have some fun. I'll help you out. All right, what three products do you get? Different products do you get when you do this reaction? Your turn. Remember, this is either tallow, white grease, which is pig's fat, tallow is beef fat, or yellow grease. And your turn. React this triglyceride with acid and water. What do you get? And when you're done, give me a thumbs up. Ah, I think everybody's done. I better give myself a thumbs up. That was lame. All right, let's take a look at this. What do we have here? We have tallow, white grease, or yellow grease. It's a triglyceride. First ester, what do you get? Here's the general reaction. You get an alcohol plus this acid, fatty acid, and this would be stearic acid. Second ester right here. You get this alcohol plus what's my R group, R sub O, you get oleic acid. And the last one, this one, you'll get this alcohol and you'll get stearic acid. So you could put a 2 there or you don't have to, because on a test, I'd ask, give the organic product or products for this reaction, which would be glycerin, stearic acid, and oleic acid. And we made that, and then we separated oleic and stearic, and we made stearic and oleic acid. Multi-million pounds per week of all those. And this is a very important reaction. I've been spell out important. Why? Because this is how your stomach breaks down fats and oils. And you should know how to describe with words in a general chemical reaction how your body breaks down fats and oils. And with words, that's acid, hydrolysis, of an ester. What functional group is in key functional group in a fat and oil? An ester. And what's the general reaction? And you can write it either way. You're probably more used to doing it this way. Take any ester, add H plus, or you can put HCl and water, and you get back the carboxylic acid plus the alcohol you would have used to make that ester, in this case, fatty acids plus glycerin. But you didn't know you were making that in your stomach right now if you had anything with fats and oils. So you should know how to describe this. Let's do another one. And this is called saponification of an ester. I'll use sodium hydroxide. You could use any base, and you get back the alcohol you would have used to make that ester, plus, because you're in base, the carboxylic acid forms the carboxylate anion, and you form this carboxylate anion. Give the organic product or products for this reaction. Your turn. Say one person's done. The other person doesn't have to rush. All the rest of you don't. All right, let's get going. And if I look at here, oh, I've got, this can be either tallow, yellow grease, or white grease. It's a triglyceride. What happens when you saponify an ester in any ester? You get an alcohol and the carboxylate anion of the carboxylic acid you would have used to make that ester. And if I look at the first ester here, what do I get? This alcohol And notice here, I get stearic acid. Next ester, I'll get this alcohol. Plus oleic acid, which I'll abbreviate like this. And finally, the last one, I'll get this alcohol. Plus, notice I'll make this again. And you don't have to write it because I asked what are the three products. You get glycerin, stearic acid, oleic acid. For those who must, you could do this or you could write it down there. Now, important thing. If I give you this or ask you this type of thing, you can use the shorthand. Now, if I ask draw the structure of stearic acid, do not use R sub S. Show all the carbons and hydrogens. So that's very important. Now, that last reaction, the last two, what happens a lot of times in people's kitchens? Their drains get clogged up. Why? Because you probably poured grease or fat down there. When I bought the house I'm in, about a month or two after I moved in, my kitchen sink clogged up. So I figured, okay, a new house. I called the Roto-Rooter guy, came in, Roto-Rooter and all that. I paid him and he said, oh, you got a 6-month guarantee. Thank you. Week later, clogged up again. I called him up. He came out. Oh, I'm sorry, and did it again. Week and a half later, clogged up again. He came out and said, I'm really sorry. Now I'm going to use these chemicals. And I said, can I look at the label? I looked at it and I saw that was pretty piddly stuff because I'm an organic chemist and knew what the ingredients were. And he routed it out, put the chemicals in there. It's clean. Guess what? A week or two later, it clogged up. I didn't even bother calling him then because it wasn't a matter of money. It was the time wasted not being at work where I was salaried, but I wanted to be at work. I figured, all right. So I go to my local Home Depot and I asked, look, there's a whole wall of drain cleaners. And a nice gentleman who worked there, and my local Home Depots, I've got two near me. One I go to in Barrington. They have great people, very knowledgeable. I said, you know, all these drain cleaners, I have a clogged kitchen drain. What's the one the plumbers use? Immediately points to this product. Oh, really? And I bought it. And let me show you what that product is. Everybody see on the screen there, the black bottle? And the black bottle has a fancy name. It's called Hair and Grease Drain Cleaner. And this is the only one in the whole shelf that comes in a heavy plastic bag. And on the plastic bag, it says use proper eye protection. Now, all the others have acid in them, H+. This one has base, sodium, potassium hydroxide. Now, important thing, and I'm going to go a minute or two late, but hang in there. It's worth the story, I hope. And the guy looked at it. Oh, this, and I picked up whatever Drano or whatever. I said, oh, this has got acid. And the drain cleaner, this has got base. He said, no, this is an acid too. I said, look, I got a PhD in synthetic organic chemistry. Trust me, I know the difference between acid and base. This is a base. And he started arguing, no, this is an acid. At that point, I learned a lesson. Never argue chemistry with someone at Home Depot. It's not worth it. I thanked him, took it home, worked like a charm. And about 10 years later, it happened again, maybe 12, 15 years later. I've been here over 20 years. I used it. I keep a bottle. I've had My brother-in-law, by the way, this works great on here, and I'll teach you the chemistry there too. This is the best. The other thing I found out from a plumber is coming out of your house, most older houses built before the 80s has cast iron pipe going to either clay or PVC to the sewer. And acids react with cast iron. Base won't. So it's even worse to put that in your, try and clean your drain out. This stuff works like a charm, never failed me. A number of my students have used it. So if you ever have a clogged kitchen drain or bathroom drain, I'll teach you later on with hair, use this. With that, I'm done for today. Don't forget, Wednesday, we'll be giving out the password for test 3. We'll have our regular class and also the lab. With that, I can say goodbye, gang gesund, be healthy. I'll see you on Wednesday. Have a nice rest of the day.